Thank you, Professor Muhammad, for an amazing talk. Professor Muhammad had actually given me one class about generative models, and it is what inspired me to get into creative AI and music. So welcome everyone. Today we're going to talk about a number of tutorials about the use of creative AI for visual art and music. Behind me, you can see the artist Sujun Chung. She's a Canadian artist based in New York, and she's a former research fellow at MIT. And she's one of the pioneers in the field of machine-human collaboration. What you can see here, she's collaborating with her own AI robotic arm to generate new art. And hopefully by the end of this tutorial, all of you are going to be able to collaborate with your own machines to create something new, whether it was visual art or music. So here's our team, Isha, DJ, Devansh, myself, Arnab, and Kalish. And today we're going to take you on a very nice, entertaining tutorials. So if you haven't done so already, I would really encourage you to go to our GitHub repository to find the links to the tutorials. I'm actually going to share that link on the chat for you to access the GitHub repository. All right, so here's our roadmap for today. First of all, we're going to start with style transfer by Isha. She's going to present to us style transfer, where you can move an image from one domain to another. You can see here the beautiful KAUST campus is being transformed into different styles. One of them is the Starry Night painting. Then we're moving to Style Can with Devansh, where you can generate high resolution creative images and paintings in one shot. Later, we're moving to Music Can with me, where we can get in the zone and generate new music, whether it was classical or different types of music. Then we're moving to Arnab, who's going to take over with Emo Style GAN, where you can input an emotion and generate an art or a piece of painting that represents that emotion. For example, the painting in front of you is represented by the emotion anger, and the generative model generated the following painting. Then Kalish is going to present to us text to art, where you can transform any piece of text into a painting or an image. As you can see here, a nice calm day for a city on the water is transformed into the image in front of you. And I honestly think it's a very good representation of that text. At the end, Devansh is going to take the presentation and present image animation, where you can animate any static image or painting into a moving one. Like, for example, here you can see the Mona Lisa is singing. All right, I hand over to you, Isha, to take us on a journey and present to us style transfer.
All right, thank you, Shaima. Can everyone please confirm that you can see my screen?
We can.
Perfect. All right, thank you. So hello everyone, my name is Isha Khurram. I am a fourth-year undergraduate student at the University of Toronto. I'm studying cognitive science and psychology, and currently I'm interning under Professor Mohammed Al-Husseini at KAUST, the King Abdullah University of Science and Technology. And like Shaima mentioned, my tutorial will be on style transfer. So today you will be learning three main topics. The first one is neural texture synthesis, the second one is neural style transfer, and the third one is something that we like to call fast neural style transfer. And you will be seeing some examples that I generated using a hands-on demo that we will all get to try out at the end of this tutorial. Before we get started, I'd like to quickly make some remarks about a topic that most of us are quite familiar on, which is AI. And we know that artificial intelligence is capable of many things, and it often completes tasks better than humans. For example, artificial intelligence tends to predict the weather more accurately than humans. It tends to derive the answer to complex questions more faster than humans, and it can even perform surgery more precisely than humans. So instead of focusing on the many areas and things that AI can do better than humans, it may be more useful to focus on the things in the areas in which AI is yet to dominate. And one of these fields is creativity. It's easy for artificial intelligence to come up with something novel just randomly, but it's very difficult for it to come up with something that is novel, unexpected, and useful. So let's go ahead and take a look at some of the ways that AI is currently being used in creative fields, such as the visual arts. So the first topic that we're going to be covering today, like mentioned earlier, is neural texture synthesis. And before I move on, I'd like to give credit to Justin Johnson. I am borrowing his slides for the next couple of slides. So the first thing I'd like to say is that the essence of neural texture synthesis is basically captured well in this question on the slide here, which is given a sample patch of some texture, can we generate a bigger image of the same texture? So you can see over here, this is an input of a small image of a texture, and the output of neural texture synthesis aims to basically generate this at a larger scale using the same texture. And in order to understand neural texture synthesis, we need to understand something called a gram matrix, which is basically how closely features are correlated with each other. It serves as a descriptor that tells us which features tend to co-occur at different positions in an image, but it importantly throws away the spatial structure of the input image, and that's very important to remember. We can perform texture synthesis using neural networks by trying to match the gram matrix of a target image using something that we like to call gradient ascent. Now, I understand that this is a text-heavy slide, but please bear with me. I'll go over all these steps quite briefly, but it'll give you a good understanding of how neural texture synthesis is actually done. The first step is to pre-train a convoluted neural network on ImageNet or any database of your liking. Then you will have a target texture image from which a new image will eventually be generated. The third step is to run the target image through the neural network and compute the gram matrices, which is what we talked about in the previous slide, for each layer of the neural network. The fourth step is to initialize the generated image from scratch, and that's what it means over here by random noise. The fifth step is to run the generated image through the same neural network and compute the gram matrices for each layer of the neural network again. And that's basically what I said in the third step, so we're pretty much repeating that. The sixth step that I like to mention is that the scalar loss function is basically the weighted sum of the Euclidean distances between the gram matrices of the original and then the generated texture images. The seventh step is to backpropagate to get the gradient of the loss with respect to the image that is being generated. The eighth step is to make a gradient step on the image that we are generating, and the last step is to basically repeat this procedure, and the hope is to generate an image that has the same gram matrices as the original image. All right, so it turns out that this procedure actually works really well. So neural texture synthesis by matching gram matrices allows us to generate and synthesize novel images that match the same texture as the input image while still looking a little bit different in terms of spatial structure. So if you take a look at the top row over here, you will see several images that we will call input images or starting images. And the bottom rows over here are images that are being generated by matching the gram matrices at different layers of the neural network. So each row represents a different layer. And if we generate images that match the gram matrices at a lower layer, as shown here, we tend to capture low-level patches of color. But as we additionally match the gram matrices from higher levels of the neural network, we tend to synthesize novel images that match the overall texture of the input image, but again, they have different spatial structures. All right, so let's go ahead and apply the theory that we learned right now about texture synthesis to neural style transfer. In simple words, neural style transfer is a class of software algorithms that manipulate digital images to adopt the appearance or visual style of another image. On this slide over here, you can see this a content image, which is a photo of these buildings. We can see a style image, which is Vincent van Gogh's infamous Starry Night, and then we see an an output image. So if we want to apply the theory that we just went over, we can basically describe neural style transfer as generating an image that matches a feature of the content image and that matches the gram matrices of the style image. And that is exactly what you see over here in the output. So using gradient ascent, we can match both these things to generate a novel image that once again matches the features of the content image and the gram matrices of the style image. So because we are using a gradient ascent approach, we will start with an image that has a random initialization, and this image is shown on the top left corner over here. And then we will perform gradual and gradient steps over time that will again gradually change the image to generate a novel image that matches, and I'll reiterate myself again because this is a key point, but it will match the features of the content image and the gram matrices of the style image. And this image over here, again, courtesy to Justin Johnson, basically shows the progress of gradient ascent over many iterations as we eventually come to and converge to a final output that you can see in the bottom right corner here. And this bottom right image is exactly the same image that you see in the previous slide as the output. All right, so while this is very cool, very interesting, and innovative, there are some drawbacks to neural style transfer, and one of them is that it's very slow and requires a lot of GPU. So a solution that we tend to use and tend to work around is something that we like to call fast neural style transfer. And fast neural style transfer is similar to neural style transfer, but there is one significant difference, is that there is a feed-forward network that is involved, and a feed-forward network basically allows the input of a content image and the output of a stylized result. So when we're training with a fast neural style transfer, the training may take some time, and that's really important to know. But after the training, all we have to do is break away this feed-forward network and simply stylize images for us in a single forward pass. And that is exactly what the demo that I will be showing you today does. Our demo is on fast neural style transfer, and I have to give courtesy to Logan Engstrom from MIT, who is currently pursuing his PhD in machine learning, as I am borrowing his pre-trained network. And his pre-trained network allows us to take any style from 6 infamous paintings, which I'll go over in the next couple of slides, and apply them to any photo that you'd like in a matter of seconds. And note that that's in a matter of seconds is bolded on this slide because that's basically what fast neural style transfer does. It allows us to work in real time. So the first style that we will be able to experiment with and that Engstrom pre-trained his network with is called the shipwreck, which was made by Joseph Mallard William Turner in 1805. And over here you can see that the style image is again the shipwreck that was pre-trained. The content image I chose for this example is the picture of a Titanic, just because I thought it was appropriate for the style image. And this is the output that was generated. And over here you can see in this GIF that I'm actually using the demo that you'll be able to play around with in a couple of moments to generate this example. And all the examples you'll see on the next couple of slides were used and generated with the demo. The next painting that he pre-trained his network with was called The Great Wave of Kanagawa by Katsushika Hokusai in 1831. Apologies if I mispronounced the name. And I took an image of a modern day surfer, and you can see the compare and contrast. I thought it would be interesting because this style image, this painting was made over 190 years ago, and it's nice to see how it compares to a modern day photo. The third image is, or the third painting or style is called The Scream by Edvard Munch. It was made in 1893. Same procedure, here's a content image, and you can see the Scream style being applied to this content image. The fourth style is called Udni by Francis Picabia. It was made in 1913. I chose a very interesting and funky looking building to match the aesthetic of the style image, and it generated this output over here. The fifth style is called Amused by the infamous Pablo Picasso. It was generated in 1935. It was made in 1935. And here I took an innocent child's hand drawing, and if you apply Pablo Picasso's Muse style on top of it, it generates this output that if Pablo Picasso himself made it, would probably have sold for millions of dollars. And the last style is called The Rain Princess. It was made by Leonid Afremov in 2014, so it's a relatively more recent piece of art. And here I took Vincent van Gogh's Starry Night, just because I thought the textures looked quite similar, and you can see the output that it generated. And again, all the examples that you are seeing were generated by me using the demo that we are about to see. This is the KAUST beacon. This is a landmark that everyone recognizes KAUST by, and I'm just trying to make the point that this works with architecture. This also works with animals here, as you can see with this very cute kitten. It also works with humans and as well as nature. So the point that I'm trying to get across is that you can take literally any photo and completely transform the way that it looks by applying a style of one of your favorite artists. So now I'm actually going to invite you, if you can and you have access to a laptop, to go ahead and head over to our GitHub repository like Shima mentioned earlier. And if you click on the link, it should lead you to this page. And these are all the links to the demos that will be shown in today's tutorial. And of course, you can click on mine over here called Style Transfer, and it should lead you to a Google Colab notebook as such. And I'll just briefly go over the basics of a Google Colab notebook for those of you who are new to it or have never used it before, because this is also my first time working with it. And it's actually very simple, so there's no need to get a little worried about it because it's very straightforward. So basically, a Google Colab notebook consists of many cells. There are two types of cells, a text cell, which you can see over here, and some code cells. And code cells contain executable code that when you run it using this play button over here, you will generate an output. So now I'm actually going to go ahead and ask you all to, if you're following along, to press play and run the first 4 cells that you see over here. Let me just go ahead and, yes. So we're gonna go ahead and run the first 4 code cells. And now I'm gonna ask you to upload 2 things. So I'm gonna invite you to now to press on this file icon over here, and you should see 2 folders. The first folder is called Fast Style Transfer, and the second one is called Sample Data. When you press on Fast Style Transfer, you should see a series of folders and some files. And I'm now asking you to go ahead and upload the train network to the checkpoint file over here. And you can access the train network on this Google Drive link over here. So once you click on it, you'll see the 6 different paintings that I went over in the presentation. And I went ahead and, already uploaded all 6 of these train networks in the interest of time, because it does take a while to upload. But again, all you have to do is download perhaps 1 or 2 in the interest of time, and upload them to the checkpoint folder by pressing these 3 dots over here. You click upload, and then you can locate them on your computer. And the next thing that I'm going to ask you to upload is your sample photos. So if you go to My Data and Train, I've already put some sample photos that you can access over here in this Google Drive folder. These are all the photos that I used in my presentation. As you can see, if you want to use your own photos, please feel free to. Just remember to use PNG or JPEG files because those work best, and then to rename the file to something very simple because you'll have to be typing up the file name later. So I went ahead and already did this, and you can see that I have 6 different train networks in my checkpoint folder and 10 different images in my train folder. So now I'm going to go ahead and run the other code cells. And now this is where the demo gets a little bit hands-on. I'm asking you to specify the name of the image file in the first line, and then specify the name of the train network file in the third line. So over here you can see that I have an image in my train data folder called Titanic.png. And let's say I don't want to generate an image of the Titanic. Let's say I want to go ahead and generate an image of a cat. So I'm going to go ahead and locate the picture of the cat that I have. And the title of it is called cat.png. So that's what I'm going to write over here. And let's say I don't want to experiment with the La Muse text style. So instead I want to try Rain Princess. So that is exactly what I'm going to type word for word. Make sure the spelling is correct. And then you're going to run this code cell and continue running. Run the main function as well. And this is where most of the magic happens in this code cell over here. And you can go ahead and review and view the original image that you had. So right now it should generate an image of the cat. And by pressing this code cell over here, you can actually see what the cat would look like with the Rain Princess style on top. So as you can see, it's very simple to use. I can go over a very quick example before I hand over the presentation to my colleague. Let's go ahead and see if we want to instead use a picture of, let's say, the beacon from KAUST. And notice that the name of the image is a JPEG file. So I'm going to write the beacon and replace PNG with JPEG. And let's say I don't want to experiment with Rain Princess. Instead, I want to try Rec. So I'm going to go ahead and only run this code cell. You don't have to run anything above because we haven't touched the code there. Now we're just gonna close this. We're gonna go ahead and run everything. And now you can see right now it still shows a picture of the cat, but when I press this, the picture of the beacon will pop up. And now when you press this code cell, you'll see the beacon with the rec style implemented on top. So as you can see, this was very simple, very straightforward, and I hope you can use this to your advantage during the hackathon. Please feel free to play around with it. And that's about it for me. Thank you everyone for listening. And now I'm going to hand over everything to my colleague, Divyansh, who is going to be covering StyleCan. Divyansh, it's over to you.
Yeah, thank you, Isha, for the beautiful presentation. I'm Divyansh, and I'm a visiting student researcher at KAUST. I've been working with Professor Mohammad El Hosseini for over a year on this domain of creativity and AI. Today, I'm going to talk about a model called StyleCan. So you just saw how to generate images, like when you have two images, a source image and a style image, and you want to, take the style of the style image over the source image, right? Or the content image. This required like two images to generate art, some level of, your own thought process, some level of manual work. But what if I don't have time and I just want to create a bunch of art pieces at once? What can I do? So for that, I use StyleCan. Notice that it generates novel images. So we will talk about it. You must be familiar with CAN using through the presentation of Professor Mohammed. As he talked about this in the presentation, we will also go over it briefly. So we will learn StyleCan step by step. First, we will learn GANs and its applications. Then we will again go briefly over creative adversarial networks for those who have joined a little bit later. Then we will talk about what StyleGAN is, and then finally we will learn what is a StyleCan, and again demo which you can try live at your own in your own laptop. So what are GANs? GANs is actually a short form for generative adversarial networks. Why generative? Because it learns a generative model. It learns to generate something. It could be an image. It could be a 3D model. It could be a mesh. It could be music. So whenever a model learns to generate something, it's a generative model. Adversarial, because it is trained in an adversarial setting. So we will talk about this very deeply in the upcoming slides. Let's let's go over it now, but we will talk about it more in the upcoming slides. Networks, because of course it uses deep neural networks for its task. It could use on like shallow networks as well, but usually the de facto standard is that GANs are usually very deep networks. Again, these slides and images are taken from several sources, as you can see on the source links on the bottom. So what are generative models? Generative models generate something, as we talked about. These are different from discriminative models, which learns to classify, let's say, a cat or a dog. So if a cat image is passed, it gives us one output, which let's say it's a cat. So it is not generating something, it's just giving an inference that, hey, I see a cat in this image. So this is a discriminative model, while generative model on the left is generating bedrooms, real images of bedrooms which do not exist, which are not photographed, but they are generated from a network. So I find GANs pretty fascinating, as they can be really they can generate really good stuff several times. First of all, why do we need such models? It turns out there are several use cases of such models. One such use case is super resolution. So how many times have you run into an issue when you have an image and you want to resize it to put in your presentation, and what you see is a pixelated version of the image after you resize, and it looks something like blurry and doesn't look good in a presentation, right? So what super resolution does is increases the resolution of the image while maintaining the content of the image. So here are two techniques which can do that. First one is SR ResNet, and the second one is SR GAN. So this is this image which needs to be super resolutioned. It is a blurry image. You can't see much into that. But using a deep neural network called SR GAN or SR ResNet, we can actually do a super resolution on this, and it is looking nice. Although it's resized, but it has also removed these checkerboard artifacts from here. It's created smooth boundaries, and this is another like higher like improved model over SR ResNet, which has created better imagery. As you can see, the water here is like not blurred. It has clear defined structures, and as you can see in the slide, it is pretty close to original. So isn't it like very cool? This is actually this image is actually taken from the paper of SR GAN, so credits to them. Next, we look at one of my favorite models called Pix2Pix. What currently you are seeing here is an example of image translation. What do I mean by image translation? Is given an input image, it will convert it into an something else but different output image. So Pix2Pix is a network which can convert an input black and white image into a colorful image. So there is a complete startup by a person, and he has also open source his repository named Deoldify, which just focuses on this aspect. So this model can do several things. Actually, it can convert your satellite imageries into like map. It can convert your semantic map into a real image. So this is like just the label of a scene in a city. So it says that these are all cars, this is a road, this is a car, and this is sky, trees, and all that. When it is trained, it can learn to convert this image into this one. It can convert your raw edges of sketch into a real looking handbag, and it can just extend from these sort of things. But what is required for training such models is that it requires a paired imagery. So for each satellite image, there needs to be a satellite image from the same location and a map from that same location, so that it can convert. So it is kind of a supervised learning problem where we have both input and output. But this model called Cycle GAN can do that in an unpaired fashion. So we do not have images of like paired horses and zebras, paired apple and oranges, but this network called Cycle GAN can use those unpaired images and learn to transfer these horses into zebras. I do not know why you would want to do that, but this model can turn an apple into an orange or vice versa. I mean, the idea of this model is so cool. I'm so flabbergasted by this algorithm. One cool example that the authors of this paper have created is converting this horse into a zebra, which looks pretty real to me actually. There are some artifacts though, but it is awesome, right? So again, this GIF image is taken from this repository. I would highly encourage you to go over the sources and really take a deeper look. But one more thing actually, we can also generate sceneries in an interactive fashion. So I define, let's say I want to create a grassland, so I draw a rough sketch and I just put it add some label to it. I draw water body, I draw sky, and I pass it through my network, and it can actually convert this into a real scenery, and it can also change the time of the day, as you can see in this GIF. Similarly, on the other side, this is actually a model image from NVIDIA Spade. It's a paper by NVIDIA which specializes in this. They propose a new layer which can do that. I would again highly encourage you to go to this page and have a deeper look. So how does GAN do it? I mean, it's interesting. If we were given this, we would require some time actually to create something from our own imagination. But how do GANs just do it like in few seconds? Um, the answer to this question lies in one of the things which I did not explain earlier, which is adversarial training. So for example, there are two people, this guy who is a forger and this another guy who's detective. But this person like not really both of them are newbies. They do not know, he does not know nothing about detective and his work. He does not know anything about forging. He does only, the thing he can do is like generate something. And this detective, the only thing he can do is just uh, classify whether if what he has seen is a real image or a generated one. So what initially this both of them are newbies and they do not know anything about it. So this person forger generates something, and the task of detective is to classify whether it is a real art or a fake art. The only signal the detective gets is that whether he was successful or not. If it is successful, he will like learn more about what real art looks like. When the fake image is passed, the detective classifies it as real or fake. And if the detective is successful, the forger gets to know that, and he has to change something in his drawing style so that he's able to fool the detective. So these two people are adversaries of each other. They're both trying to fool each other. They're both trying to outclass each other, right? So that kind of playing a game. And when they do this several times, like they just generate millions of paintings, and detective also classify millions of paintings, and they receive the signal whether they were successful or not. They learn. What they do is actually learn. This person becomes the better at his job. This person becomes better at his job. uh, so this is the beauty of this adversarial training. Like in we can take an example of competition. If two people, there's like two highly competitive companies, they're both trying to become better, and as long as they're both trying to become better, they both will grow. We can take example of Messi and Ronaldo. They both try to outclass each other in every game, but they both become so wonderful players, right? So this is something called an adversarial training. So this is a like a layman example, but what actually happens, there are two deep neural networks, which is generator and another one is discriminator. As you can see, the input to generator are just random numbers, and it generates something. Initially it will just generate something random, and the input to discriminator could be a real art, or a real image or a generated image. If it is real, it should classify it as real. That's the signal that it will get that you were successful. But if the generated image is passed, it should be able to classify it as fake. And the generator also gets to know whether it was successful or not. So in this process, when lots of training steps happens, so for example, if we are training on art data, if it sees lots of art images, and it learns to classify what art images look like. On this, like on the other hand, this generator also learns to generate images which looks like actual art. So this is the magic of adversarial training. So now that we know GANs, I will just briefly go over creative adversarial networks, as it was previously covered by our professor in his presentation. Um, so it is actually a paper by him only in 2017, which in this paper they use this data set called wiki art, which contains 80,000 art pieces, real art pieces, which also has their styles associated with them. So for example, painting, and let's say it's style cubism, or maybe minimalism, realism, something like that. So what the paper says is that traditional GANs are emulative. What do we mean by that? Is that suppose a GAN is learning from, let's say, two types of style, realism and cubism. If it has only seen only those two styles, what it will generate will be new, but it will produce from the same style. It will either generate cubism or realism, something like that. But it does not want to be, go beyond those boundaries of the things what it has seen. But we want the generator to be creative and explore spaces beyond the established art styles. So this WikiArt dataset contains actually 27 art styles. So the generator will have to learn to go beyond these 27 art styles. So as we talked about, this objective of a GAN model, which is real fake objective. So another objective is added, which is like different for both the models. If a real image is passed into the discriminator, of course, it has to learn to classify it as if it is real art or not real art. It should also be able to classify which art style it belongs to. And if the generated image is passed, the discriminator should be able to classify it as art or not art, but it should get confused while classifying which class it belongs to. As you can see, these two forces, like real fake objective and this ambiguity objective, are two contradictory forces. Because when so for example, for generator, it needs to learn to generate an art which the discriminator classifies that, yeah, this is an art piece. But at the same time, it should say, oh, I don't know what style it belongs to. So this is the objective of the discriminator in this. And using this process, the generator becomes creative as it learns to explore the spaces beyond established art styles. So we covered 2 points. First, GANs. Second, creative adversarial network. Our third step before style GAN is style GAN. So what is style GAN? It is a very advanced version of generative adversarial networks. It has very carefully designed these generator and discriminator networks. And the best of all is that it generates very high quality generations. So to look at some of the generations, to assess some of its quality, these are some of the faces that it has generated. To be honest, I'm surprised how good they are. Believe me or not, these are real cars. When I first, I had a glance over them, I was like, are they real cars? But actually all of them are not real. They are generated. They are not photographed. Again, these are not photographed bedrooms. These are all generated by a style GAN. So let's play a game. I will give you, let's say, few seconds to classify which face is real. Okay, the time is up. Let's look at the results. The right one is real. I'm pretty sure that many of you must have considered this woman to be the real one. I myself confused this woman to be the real one. So, but actually this man was like the real image. This is actually a generated face. I was this is how like this how good these style GANs are. This just tells us, right? This example. So it can confuse us, the humans. But there are ways of, of course, going around this and looking for specific patterns that GANs have. But we will not go into that. I would encourage you to go into this website, which is called whichfaceisreal.com, and play it for yourself, right? And see like how good are you at classifying real versus fake. So we know style GANs, scans, style GAN. So what if we combine style GAN and the GAN objective? What should we call it? We call it style GAN, right? So let's look at one of the example of style GAN, and I would highly encourage you to again go on this repository here. Oops, yeah. Go on this repository here, click on this demo, and it will take you this page. All right. Yeah. So as you can see, there are some, Isha gave a very beautiful introduction to Google Colab. So I will just start with my demo. So this is first cloning the GitHub repository, which actually contains the architecture of the GANs. So I will run this by clicking on this play button, and it will take some time initially. Okay. So I was running another demo. So it asked me to terminate that. So I will terminate it. And it has, I think, cloned the repository. Okay, I'll have to run it again. So if you get something like that, just click on terminate. As you can see, it is creating some files. This will actually download this repository and put it here in my local disk, which I can access later. At the same time, I will also download a model which we have already pre-trained on StyleGAN objective. I will just refresh this folder. And as you can see, I have the pre-trained model here. I have the style-based GAN PyTorch, the model here, the model description architecture here. I will run some code files so that I'm able to access these as libraries. So I'll import some libraries for some, dumping of images to calculate something, import standard math Python libraries. Here is the style GAN generator, which I am importing. This is the architecture which I'm importing. I've yet not loaded the trained model. I'm importing some libraries like Torch, which is actually a neural network library. You can use it to train neural networks, and some plotting libraries. As you'll see, it will come handy in plotting the result right here in the notebook. So I'll set the model path, which is this model. This is some latent code size, which is some hyperparameter of the model. So it was trained using 512. So I will have to set it to 512 here. It was trained on 256 sized image. So I will have to set it to 256 sized. The only thing that I can change is how many of them I want to generate. So I'll run this cell. I will generate like 3 rows and 5 columns of notebook, art pieces. And I will just like define some helper functions. Actually, these are functions from this repository. Okay. I did not run this. So I'm getting this torch not defined error. So if you get something like that, just run the import statement, and it will import all the libraries for you. Now, when I will run it, it works just fine. So here I'm defining that I want to use the GPU, and I'm defining the style generator, and I'm initializing it with the latent code size. I'm importing the model here, and I'm putting into evaluation mode. Notice that we are not training now, we are just using it to inference. So I'm putting it into evaluation mode. So I'm using the size to compute some hyperparameters of the model. So I'm calling this my helper function to get a variable which will help me in generation. The sample function is actually the generator. It will use this generator architecture, which I initialized here, to generate n rows and n column of images. And these are just some helper code lines to plot this. So let's see what it generates now. So guys and girls, these are all novel generated images right in front of you. I can run it again, and it will generate again totally new, totally brand new images for you at each second. You can use it to do your own thing. Maybe have it printed out and maybe use one of the super resolution technique to, increase the size of the image and have it collage or something. And if you want to generate like thousands of these, you can just run this code cell and it will generate like as many as you want. Just you have to change the number here. So this is as simple as it gets to generate a novel art. So this ends my presentation, and I will hand it over to my colleague, Shaima, who will talk about Music Can. Over to you, Shaima.
Hello, everyone. Can you hear me?
Yes, we can hear you.
All right. Thank you so much, DJ, for an amazing presentation. Really loved that tutorial. And also, thank you all for sharing your generated images and participating in the tutorials. All right. So today I'm going to be presenting to you Music Can, which stands for Music Creative Adversarial Network. Let's look at the outline. First, I'm going to talk about the motivation behind this project. We're going to take a look at the dataset, the network architecture, sigmoid versus hard sigmoid, which is the activation function for the last layer of our model. And then we're going to look at unrolling our can and ending up with a demonstration where you can generate your own music. All right, so the motivation. Why are people very interested in generating music? Well, currently it's a very hot topic. A lot of people are trying to understand what makes music sound good and how can we generate new music and learn how to do that. It's a different challenge than natural language processing, as it has other aspects to attend to, like rhythm and polyphony. The data set I used for this project is a set of classical music called MusicNet, where each collection is classified by the name of the composer who had composed this these number of musical pieces, like Beethoven and Mozart. The data set is transformed from MIDI files into images, and you can think of it as a musical note grid. Like, for example, if a pixel was high or is equal to 1, then the musical note at that position is on and you can hear it. Otherwise, if it's 0, then there is no musical note being played at that position. So let's move to the network architecture. You've already learned about the GAN network from DJ and the Professor Muhammad. And now I'm going to give you another explanation of it, or to refresh your memory. This is the CAN network architecture, and it's very similar to that of the GAN network. What you have is a Z vector that is random, passed to the generator. The generator generates a musical piece or a music file and a label. The discriminator always gets as an input a musical file and a label, whether it was coming from the generator or from your dataset. The discriminator then tries to figure out whether this is a real musical piece or a generated musical piece. So here we have your regular GAN loss. And then there's another loss that we're looking at, which is the entropy, where we're trying to make our network creative. What we're trying to do here, we're trying to classify the musical piece. And what we're trying to do, we're trying to look if it fits into one or more label. So in a way, you can think about it, we're trying to maximize the entropy between the classes. So a musical piece, we want the generated musical piece, we would want it to have a class that is either different, we haven't seen it before, or if it falls between two different classes, like it sounds something like Mozart and something like Beethoven in between, That's what the entropy loss is trying to do, and it's trying to promote creativity in the network. So remember I told you we're going to talk about sigmoid versus hard sigmoid? Well, while I was trying to pre-train the model, I looked at the output, and I had a lot of gray areas. And gray areas, remember when I talked about the data set, we had either zeros or ones in our data set. So the discriminator can see the zeros and ones. The generator has to generate the zeros and ones to look like the real images. However, with the sigmoid being the last layer or the last activation function in the generator, we end up having values between 0 and 1 most of the time, and some of them are either 0 or 1. What we would like to use is the binary step for our data set. However, the binary step, as y'all know, it's non-differentiable because we have a discontinuity here. So the hard sigmoid, in my opinion, worked better because it has more probability of giving you zeros or ones and less probability of giving you other numbers in between, giving us the gray areas. And this gives the generator a way or a help to create images that can fool the discriminator. All right, now let's talk about unrolling our can. So before we learn about how to unroll cans, let's understand what unrolling helps with. What problem does it solve? So on the far left, right, you can see the targets. The targets here are our data set. You can think of them as our data set that we would want to generate. And the outputs here are coming from generators. The second row shows a normal generator. This generator, whenever it tries to generate sample files or images, it's always generating one mode that falls within the target. For example, here, it's focusing on this mode. And when it does that, it is still being rewarded. It is still doing good, and it's still beating the discriminator because it is generating something that is within our real data. However, it is not capturing the full distribution, and it's not mimicking the distribution of our data set. When we unroll our generator or our model, you can see in the first row here, the model is more capable of generating all the modes. And that's why we call it mode collapse, or the issue is called mode collapse, because it can only generate one mode if it's not unrolled. And unrolling is one way to help stop that issue from happening and represent the same distribution. Another example that can help you understand what I'm talking about is a generator or a model that has been pre-trained on the MNIST dataset. Again, the first row is the unrolled model, and the second row is the regular model. You can see in the regular model, it sometimes or always gets stuck in one of the modes, and that's what we call mode collapse. Why am I applying this to the music generation or the music can? The music generation model. That is because I've been facing a lot of problems with the generator generating black images. And that is because when it generates black images, the discriminator thinks it's real music. But I don't want that to happen because then I'm not having any music to listen to. And that's how unrolling helps. But how does it work? What you want to do is you want to train regularly, like you do with any GAN or CAN model. But you can choose your unrolling steps. And what that does is when you generate the new generator, or when you train the new generator and the new discriminator, what you want to do is back up the discriminator. This way, your generator has look-aheads or can see the future of what the discriminator will look like. And the discriminator is always behind. That helps us from having a very well discriminator or a very strong discriminator so that the generator can catch up and figure out what to do before it collapses into one mode and cannot produce any more results. All right. So enough of the theory, let's move to the demo. I will show you now how to create your own music and try both hard sigmoid and sigmoid activation functions to figure out which one you like best. So you're not an expert musician, huh? No problem. We've got you covered. Please go to your to the GitHub repository and find the Google Colab notebook. We've already shared that on the chat, and you can also find it on our dev post. Okay, now I will share with you my Google Colab. Okay, can you see my Google Colab?
Yep.
All right.
Yes.
So in the first cell, I'm going to load some libraries. And because I'm mounting to my G drive, as Isha had shown you before, it might ask me to give it an access permission. So you can all follow along, and if you have any questions, please let me know. I can help. So here I'm loading some libraries and cloning my repository that contains the pre-trained models. And also it contains some images and data sets that you can use to train your own model. Okay. I want you to check that you have 1.9 PyTorch version. Here, I'm previewing some of the data set, some of the images, and they are MIDI files that have been converted into images. You can go and visit this Wikipedia page to learn more about MIDI, which stands for Musical Instrument Digital Interface. In this cell, I'm initializing the generator and the discriminator. Also, if you're not very familiar with this type of cell, you can click on show code to visualize the code or just read the text. Then I'm loading a pre-trained model. It's unrolled, but it uses Sigmoid. In this cell, here is where you can experiment with generating music. When you click on the cell or when you run the cell, you're always going to get a new generated music. If you don't like it, you can generate it again. Okay, we can listen to this musical piece. All right. And if you like your musical piece, you can download it. Now let's look at the pre-trained model with hard sigmoid. In my opinion, I think hard sigmoid does a better job, but it's up to you to choose which one you like. All right, let's listen to it together. Okay, and then the rest of the cells are for you to pre-train your own or to train your own model. Here I'm setting some hyperparameters, loading some all of the images I have, and you can experiment with them and train. So an idea for you to try, you can also change the data set from the classical music data set into different types of music. Like you can, for example, mash up some Arabic music with classical music and find out what you can generate. Okay, now I would hand over the presentation to Arnab, where he will be showing us emo style GAN. Arnab, are you there?
Yep, I'm ready.
Okay,
Okay,
floor is yours.
here we go. Sure. 1 second. Hyperlink. There we go. Okay. So emotion style GAN, conditional generation of visual art. By using our previous knowledge of style GAN, emo style GAN uses style GAN 2, which is an iteration of the style GAN which Divyansh talked about, which comes with adaptive discriminator augmentation. It uses the Artemis dataset, which is an extension of the WikiArt dataset for training with conditional classification for these 8 specific emotions. So this dataset allows us to generate images with amusement, anger, awe, contentment, disgust, excitement, fear, and sadness. So how does StyleGAN 2 work? As we can see here with this diagram, this is how StyleGAN 1 worked, the previous iteration. It would take the mean and the standard deviation of both of the inputs and the outputs to create and put them inside a style block by taking our real to generate our fake real and fake images with our descriptors. However, StyleGAN 2 instead of using mean and standard deviation, just uses standard deviation and allows for analog inputs as well as digital inputs and digital outputs, analog outputs. By putting the inputs and the outputs all into the style block instead of being separated from outside the style block. It also allows for weight demodulation, which allows for weighted pathways for the generation of the images to preemptively generate, preemptively force the code to guess which image would be the best when trying to fake the detective, as Divyansh put in his example. So what is adaptive discriminator augmentation? It is a technique created by NVIDIA to allow smaller data sets to still create accurate images. As we can see here, this is from the NVIDIA Labs GitHub for StyleGAN 2 ADA for PyTorch, and allows us to use this cat by allowing for small data sets to create images such as the cats here with the discriminators and the generators, with the augmentations, as we can see here from this diagram. The Artemis dataset is an extension of the WikiArt dataset, as I've stated before, which comes with emotion labels for conditional training. It comes with emotions. It comes with a CSV like this, which comes with a painting name such as Alagoma in November from 1935, created by Jackson, and we can see by A.Y. Jackson, and we can see this image here that I've highlighted. We can see the same thing here with Jackson Barnes, 1926. Here is, while training, here is the fake artwork collage generated by the Artemis dataset. Each of these 480 images inside this collage has been generated by the AI and is not, and is a fake image. So, conditional training. This AI model has been trained with conditional text, which allows us to generate images based on the 8 specific emotions, with a different image being generated at each moment. For example, we see here, we have amusement, anger, awe, contentment, disgust, excitement, fear, and sadness. I'll be opening these up more to show examples between each. So when we put into the code, where we want to generate the emotion of excitement, the code generates an image like this, which has a jumble of elements inside the image, which creates excitement as it's not really contained. However, fear, we can see, is more from the portrait, much more darker colors, and from the facial expressions, we can see the eyes are bigger and the mouth is more tight-lipped, which allows for more fear. Here's contentment versus disgust. Contentment, we've got blue skies, some nice trees, and a picnic-like setting. And the person in the image is relaxed and brings to the viewer also contentment. Versus in disgust. as we can see, much more darker background. The lips are much more frowning. The eyes are much more slightly small, squinting, and the body language kind of is leaned backward as if they're repulsed. And we have the same thing here for amusement and sadness. There isn't much of a difference between amusement and sadness, which is, I figure, a problem with the AI model that I've trained. However, we can see from amusement, well, it turns out these images are in the wrong way. Here that I've highlighted, which I'm circling around my mouse right now, is amusement. You can see this from the mouth being upturned slightly, lips are slightly upwards, eyes are more open, and the person is enjoying and it's amusing. The person in the photo is finding whatever they're looking at amusing. However, for sadness, as you can see, the eyes are much more droopy. They're in more of an angle, and the mouth is much more tight-lipped again, and much more close together, and putting pressure on top of the two lips, which creates more of a sadness, which forces us to feel sad. Now we have the demo and hands-on. If you would like to visit the collab, which was on the GitHub repo and the README, we can first set up environments and variables. I hope that it should be set up for you. However, if it is not, I'm sorry, but you'll have to wait several minutes just to install PyTorch. StyleGAN 2 does not work with PyTorch, the latest version of PyTorch, which is 1.9, which is why we have to install 1.8.1. If you'd like to run that now, while I would explain to the code, that is fine. That'll be helpful. So here we have, I've already pre-installed it here in preparation for this event. So first we have an import of StyleGAN 2 ADAs from their GitHub, from cloning from this line right here. This cloning allows us to use their custom Torch utils, which connects with CUDA and their custom CUDA code, which allows us to generate and train the AI model. As we can see here, when we generate, we have sys.path, and we have pulled in, so that allows us to import stuff like legacy and DNNL-lib, which was written by NVIDIA. And we also have this dictionary right here. This is just so when you type amusement in the generation code below, it gives the class. So this is the conditional training of the AI model. It uses, so of a class 0, it is amusement. For a class of 1, it is anger. We can see this with the CV from the data set right here. It has got amusement, anger, awe, contentment, disgust, excitement, fear, and sadness. And we can see that in the AI, we use something called dataset labels file, which is called dataset.json. And it was mapped as this, as the amusement column as 0, anger as 1, awe as 2, and so on. And that is just mapped to here. And allows you to write as a string, let's say sadness, and it'll just automatically map just to make your life easier. So we import from Google Drive the network snapshot here, this network for the AI trained model, which can be used to generate. Then we just have some ranges. This is just which seed you would like to use. I have set here seed 10 because it has very nice portraits to show the facial expressions. However, you've got access to 480 seeds because each seed is an image from the collage right here, and there's 480 images in this collage. So you can generate up to 480 seeds, and that gives you a large range of images to mess around with. So here we have the generate function, where we're using CUDA and the custom code written by NVIDIA to create images here, which can be found in image generation in the file section. there is also a label with what seed and the name of what emotion. So now you can generate your image. So here we import matplotlib for you to be able to see the images here that you've generated. We give it a truncation because this is a pickled file, which means its data is extremely condensed, and the truncation allows the code to kind of unpack the model to be able to use it. So, and I also have a few pre-generated images as you wait using C27, which generate images such as this for sadness, this for anger, because a lot of red anger kind of looks like blood. I don't know why, but and amusement here, as we can see. And that's about it. I'd like to now hand it off to Kalishbek for text to art.
Hi guys, can you see my screen?
Yep.
So thank you, Arna, for your amazing work. And hi everyone, my name is Kilic. I am a PhD student at the King Abdullah University of Science and Technology under supervision of Professor El Hosseini. And thank you, Arna. Previously, you explained, like introduced your cool work, how to generate art images given conditional, some emotional labels. Now let's imagine that we want to generate synthesized images conditioned on some textual information. So it can be captions, or it can be a word, or it can be like a poem or some part of a lyric. So my topic will be about this text to art generation. So in general, like briefly, to generate images, we need some, of course, like as an input, a textual description. Here you can see the mountain seems to be floating in the lake. And we need some like text encoder, which helps us to represent the text in a way that that is easier for generative models to understand, analyze, and process this piece of information. And also, of course, like is the main model, the generative models. So which is used to generate, synthesize a piece of art. So here you can see if we supply the mountain seems to be floating in the lake to text encoder, text encoder will generate text embeddings, and text embeddings will be used for in generative model to generate this kind of beautiful image. Of course, this is hypothetical view, like hypothetical output, but in general, we want this kind of output. So a lot of research have been done in text-to-image area. So one of the examples of state-of-the-art methods was attention GAN. So here we trained the attention GAN model on our Artemis dataset, which was explained by Professor El Hosseini and Arnab. And here you can see some of its generations. I present here like it's four outputs. First one is the man's tired eyes make him look like he has spent many hours in front of a book. So you can see it generates some like a creepy picture. And as well as like, if you can see a nice, if we give a nice column day for a city on the water as an input, the generator tries to generate some silhouette of the city, which closely matches to a given textual information, which is like some water and silhouette of the city. And so on January 5th, 2021 of this year, you guys might be familiar with OpenAI. So OpenAI released the model weights and the code for CLIP, which is like trained on really large data set, around 400 million of image and text pairs. And as a consequence of this multi-modality training, CLIP can be used to find the text caption that best represents a given image or the most suitable image given a text query. So after OpenAI released after OpenAI released their model, there was a boom in AI community, and various hackers, artists, and even like deep learning enthusiasts started to they figured out how to utilize this like powerful model clip as a guide, as a natural language steering wheel for various generative models. And this in turn allowed artists to create all sorts of interesting visual art by inputting some text information. So here I will briefly describe clip-based models. This is like a really high-level depiction of how clip can be used to generate art, because we don't have that much time. So basically we have two models, big GAN, like some generative model. It can be used, it can be any generative model, GANs, like big GAN, SAAI GAN, or VQ GAN, and even Siren. So, and we have a clip model. Clip model just computes embedded similarity measurement. But for that, we need some output from generative model. Generative model tries to generate some image. So this image will be given to a clip image embedder, and this embedder will image embedder will generate some embeddings. And the textual information will go to clip text embedder, and clip text embedder will also generate the tries to map this image embedder, and text embedder tries to map like inputs to the same like project to the same space. So in this way, we obtain two embeddings and try to compute similarity measurement. So, and we want to maximize this similarity metric, and once we compute the similarity metric, we will give feedback to the generator how close we are to the textual description, or how far we are away. In this way, we try to optimize the output of this image. So yeah, based on this approach, like Ryan, the person called Ryan Murdoch came up with an idea to combine clip model and Siren as a generative model. So, and he called his idea Deep Days, which is like a cool name. So here two generations of this method, Deep Days, a time traveler in the crowd and mist over green hills. So why he called this method as a Deep Days? Because the images have a fever dream, or like a hazy quality, as you can see here. And then the same person came up with another idea. So he proposed a new approach, which is called the Big Sleep. So the idea is similar to the previous approach. It is also uses a clip model, but this time instead of Siren model, he uses like a big GAN, the generator of the big GAN. So he just replaced the big GAN model, like Siren model, with the big GAN model. So as you can see, like we have much more images of higher quality, and the images here have a strange dreamlike quality. So that's why he called it Big Sleep. And then Catherine Carlson finally she reveals her attempt to combine VQ GAN and clip together. And here also you can see really high quality generations from her model, her method. And one interesting aspect of this approach is that it allows specifying an image as an input starting point. And if you take the output of the generator and stretch it very slightly, and then feed it back again into the system, you'll take slightly closer resembling outputs. And if you save these outputs as a frame, you'll end up with a movie with a zoom in effect. So if you jump to our provided Google Colabs notebooks, you can play around with the text to image generation. And first one is the attention GAN model. So we provide pre-trained models already. So just you need to execute cells step by step, consequently. And I already executed them. And if you provide here captions, you can obtain the generation from the attention GAN. So here, the example is the man's face looks sad. So the output, it is again, some creepy person, I would say. Yes. And another example, the mountain looks beautiful. So the generator tries to generate some mountain, and which like corresponds to this caption. And then at this point, you may, for example, restart your runtime, because you may run out of the RAM. So if you click restart runtime, and then click again, install Deep Days package, which was provided by Phil Wang. And here it is more interactive. You can place your text description and specify number of layers, and also specify the resolution of the output of the generator. And you can like get like generations, so after some iterations. And the same goes to Big Sleep. So Big Sleep is also provided by this famous like a Phil Wang, who's contributed to this repository. And here is the same text description, but this time the image quality is much more higher because it uses more advanced generator. So thank you very much. And now I will hand over presentation to Divyansh again, and he will explain about image animation. Thank you very much.
Thank you. Can you hear me?
Yes, we can.
Yes.
Oh, thank you. I will not bore you guys with my introduction again. I will quickly jump to the fun part. Now we will talk about image animation. Image animation, like, I'm sorry, is a very common term. It can be of several types and can be done using, there are several types of software, but I mean, we are talking about creative AI. So the type of image animation we are talking about will be done using an AI, where there is a static image, which we also call the source image. We will make a video using that static image using a driving video. So there is a driving video, and that driving video will generate use the source image to generate the final video. What I mean is that these are all the source images. So these are all static images, and this is our driving video of a famous person, and these are source images of a famous TV show. As you can see, this driving video is able to drive all of these source images into these image animations. As you can see, they are also able to mimic the little eye blink that we see. So I find these models pretty fascinating. Again, this example is taken from this place by Alexander Sayorin, and we will talk about their approach later on. This type of image animation can also be applied to human poses. So this is the driving video here, and these are all the source images. These source images are being driven by this video, and they're all like able to imitate the source, I mean the driving video, very well. Not only to faces or poses, it can be applied to any class of object, in this case stickers. So this driving video is animating all of these source images. As you can see there, if you look closely, you may find discrepancies a bit, but overall it's doing quite a good job. So we do all of this by using something called a first order motion. It is again the model proposed by Alexander Sayorin, and we will look how they do it. First of all, the key features of this model. First is that it is completely unsupervised. So it does not require any label. So if it were a supervised problem, we would require a driving video frame, then a frame of same pose of this person, and then we would be able to do it. But no, in this case, if we want to train, let's say for faces, we will just require a bunch of face videos. Let's say if we want to train on human poses, we will just require a bunch of human videos. stickers, then sticker videos. So this is completely unsupervised and does not require any label. So the previous work prior to this work, the first order motion model work, required like the landmarks of like places. So if it were animating like faces, it required landmark of like eyes or let's say mouth, nose, to train it for the training step. But this model even does not require that. So how does it do it? So there are two parts of this model. First is motion extraction and another is generation. So as you can, like, you must be understanding that this motion extraction is responsible for extracting the motion from this driving video. Actually, it's not a video at this point of time. It's actually a frame. So it extracts the motion of this frame. It compares the motion with the actual source image, and it gives us a dense motion map. You may see that there it also extracts key points in between. So it learns the key points of all several type of class of objects on its own in an unsupervised way. We get a dense motion map and an occlusion map. Occlusion map is required, for example, if there's occlusion of the object in the driving video, this occlusion map takes care of that, so that the source image is generated using the context of the source image, not the driving video. So this generation model contains an encoder. After the image is encoded, it is warped using this motion map. And if there are any occlusions, it is multiplied with this warped image. And then finally it is decoded. As you can see, this source image has been successfully converted into a similar pose as the driving frame. If you want to look how it will look over a certain number of iterations, let's look over it. So this is a little animation that I created, and this is how it works. So pretty neat and pretty pretty nice model. I really liked it. I've taken this slide from the YouTube video that the author uses to explain. Again, Alexander Sayorin. I'm sorry if I'm pronouncing it incorrectly. So now we also have a demo for this on Collab. Thanks to the authors who have prepared this wonderful interactive notebook, which we can, oh, oops, I stopped sharing my screen. Let me share again. So thanks to the author of this model who prepared this wonderful notebook, and let's reconnect our runtime. Okay, I'll close the notebook and this. So if you run this, first again, it will install some libraries. And if you run this cell, it will create a web interface right here in the notebook for you. So the web interface looks something like this. So you can select people's, cartoons, dolls. You can animate Annabelle as well, by the way, or maybe the It Monster, Game of Thrones characters, statues. So there are all sort of options available. You can upload a custom image as well, and there are some driving videos. Actually, I will stop sharing again. I will share so that I optimize for video clip. Yeah. So once this is done, I will select Mona Lisa and I will select this person's video. And once you run this cell, you will also get this interface, and you can select people and just click on generate. And it takes around 3 to 4 minutes to generate. So in the interest of time, I've already generated and put it here. So let's look at how the generations look like. Pretty neat, isn't it? I find it really amusing and really funny. Seeing Mona Lisa sing. Leonardo da Vinci would be proud of her. So let's present again. So we tried it on Google Colab. I highly encourage you to do that yourselves, and feel free to play with the notebook and extract out the key parts. So now we will look at the example where this is, I think, a speech of Leonardo DiCaprio from Oscars, and we just use Mr. Bean to imitate him. So let's see how it looks like. Quite cool, right? So this is how we can use any source image and animate it using any video. But make sure they are of the same class. If you are using a face model, this should be of the face class. And if you're using a pose model, it should be the pose class. All the options are in the notebook. Finally, I will now introduce our final speaker. I think the most important one for you to conclude all of these demos and presentations.
This example now concludes our presentation. All the best for the SAAI Factory hackathon. It is now time for question and answer.
Thank you, Mona Lisa, for concluding. So again, summing up, these are all the things that we went through. So for all the resources, you can maybe copy this link, and this link should be in the chat as well, and also on the SAAI Factory Dev Post website. Please, I would highly encourage you to look at these tutorials and just mess with it and have fun.
At the end, we would like to acknowledge Professor Mohammed Al-Husseini. Thank you for all the time and the meetings and the mentoring you've given us. Thank you for always being supportive.
Thank you. That was a surprise.
Thank you, Professor.
All right. All right. Thanks so much for all your hard work to make this possible. And I want to share with the audience that if you have any questions, you feel free to play with this on GitHub. We can easily go on a Google Colab and just run the cells themselves and play with different options. And I hope that you enjoy the rest of the hackathon. We have yet to come a lot of exciting talks and exciting programs for the rest of the day and for tomorrow as well.